Hello, I want to demonstrate today how to do finite element simulations with Simcenter 3D or NX for electric thermal heating of conductors, electric conductors. We use two solvers. We use the NX magnetic solver from company Dr. Binde Engineers, and we use the thermal flow solver that comes from MAYA. Both are implemented in NX or in Simcenter 3D. Look at the first picture here at the top. This one shows the electromagnetic simulation of the two conductors with alternating current at 50 Hertz flowing through the two conductors. You see the effect of the skin effect because of the frequency. The electric current goes to the border of the geometry. This electric current produces losses. We call them eddy-current losses, and these losses are then transferred to a thermal solution with the thermal flow solver, and the thermal solution computes the temperature field. You see here the temperature rises between 41 and 44 degrees, and the hottest points are here in the middle, because in the middle, at the interface between these two conductors, we will have an additional contact resistance. How do we set up such a model? Let's start from scratch. So I open a CAD model that shows how we could start with. You only have a block for the air, a block for the first conductor, and another block for the next conductor. I would recommend to give names to these geometries, but don't simply give the names to the features. What you see here are the features. Give the names to the volumes. And to do that, make right mouse button here on this part navigator, switch off the timestamp order. So you have it on now. So these are the feature names. Switch it off. So here you see the volume names. So now take the first one, give a new name, air, for example. The second one, we call him copper 1. And the third one, we call him copper 2, for example. So, and you can, if you want, go back to the timestamp order to see the feature names. These are the feature names. Or you can go to the switched off timestamp order, and then you see the volume names. And this is now responsible for the following names. In NX pre-post, you will have the system now use these names and apply them to the meshes. And this makes it much easier to work. One thing that you need is in the customer defaults, one setting. Go to simulation, pre-post, meshing, and take care that this one is activated. Use polygon body names for meshes. If this one is activated, it will behave in the way that I will show to you. So let's go to simulation, application, pre-post. We want to start with the electromagnetic simulation. So normally we would do a new FEM and simulation to create the FEM file and the SIM file. We want to additionally now use a new feature that is called non-manifold geometry. This new feature is available in the newer versions of Simcenter 3D. And to use this in magnetics, the best way is to use a button that we have activated here that is called New FEM and SIM with non-manifold. And if we use this one, the system will automatically create the FEM file and the SIM file and also the idealized file. It will activate this non-manifold feature, and additionally it will use templates for the FEM file, and these templates will already contain some basic materials. So this makes it much easier to work, and so the recommendation is now in this newest version 22.12 to use this button New FEM and SIM. Let's check for the version quickly. You see here the version is 22.12. This is the version where we have this non-manifold feature now in that way available. So what we do is we simply make a new fem and sim, and the system creates the fem and the sim file for us automatically, and the non-manifold feature is active. So you see here we have the sim file, we have the fem file, we have here the idealized part, and we have our cut geometry. Let's go to the fem file. So in the fem file, check that we have already some basic information here. We have already a basic air material. So for later creating meshes with air, we simply will put them into this collector, and this collector already has the properties that we need. The fluid, physical, and the material property for air is already there. And another thing here, if you look into the groups, there is a group that is called non-manifold phase, and if you look at these members of this group, you see that these phases that belong to the copper and that are bordering the air, these are the phases that are selected for the non-manifold phase. So all the phases where we want to have a conformal mesh, so the nodes will be connected from the copper to the air, all these phases are those where you in the prior versions would have to create mesh mating conditions. But in this version, this is not necessary anymore. You simply use this non-manifold approach. Let's start with meshing. So let's blank the air and start meshing these two copper parts. Like always, we take tetraedal elements in many cases. Hexaedals are also possible, or maybe others. Take this one. First go to reset the dialog to the origin, and now start with the first one. I would recommend to use this automatic element size, and I recommend to write an expression name here. I always call this mesh factor, and I set this to a value that I want. For example, a value of 0.25 would mean the default value divided by 4. And this is a good one for quite fine mesh. So this is the first mesh that has been created. It's still coarse, but for this basic example it should be okay. Let's take the second one. Use the same mesh factor again. Simply say OK. So we have the second mesh. It's also coarse. Let's take the air mesh, so make this one visible. Take this one and also use this mesh factor, but now with the destination collector switch off the automatic creation and select the one that is already there for air. So, and quickly we have a mesh for our geometry, and if you look at the connections, these areas, you see that the nodes from the conductor are connected to the nodes of the air. So this is what we would priorly have done with mesh mating conditions. Make this one invisible, and let's look into the area where these two overlap. And you see also here the nodes of the first conductor and the second conductor are coincident. So this is done by the non-manifold geometry that we are using. So let's look at the material properties. You see we have names here for the meshes, and these names have automatically be taken from the polygon geometry names, and these names again are taken from the cut geometry names that we have applied there. The air is already completed. We don't need to do anything here. The copper 2 and copper 1 must be modified. So let's edit the copper 2. Edit again. And see, the only thing that we need is material here. And we can see now we already have some basic materials available. This is because of the template that has been used. There is already a basic air, there is a basic aluminium material, there is a basic copper material, and there is a permanent magnet, this one. And then there is one for electric permittivity, for electrical simulations, and there's one with magnetic permeability of 1000 to a core material, for example. So basic materials are available, and if this is not enough, of course you can always go to this one to choose a new material from the big library. So in this case we choose the copper material, and the same we do for the other one, copper 1. We also choose the basic copper material. So, and that's all we need for the FEM part. Let's go to the simulation part. So in the simulation part, maybe we blank the meshes for easier selection. We want to do, the first thing we have to do is creating a solution for magnetics. Let's call this magnetics maybe DC, because we want to do, RAC, we want to do an alternating current solution. So we have to take the solution type magnetodynamic frequency, create the solution, and first thing is output requests that we have to think about. Let's activate the eddy current losses density. This is the most important thing for computing losses that we want to transfer to the thermal flow solver. Additionally, maybe we want to have electric potential available to see the voltage drop over the geometry. And maybe you wanted to have some tabular results, some overall integral results. Let's also activate eddy current losses here to see the overall losses on the first conductor, on the second conductor, and maybe on the interface area. So in the frequency we have to define the forcing frequencies. So we must define our main frequency of 50 Hertz that we probably will use here. And in the coupled thermal we maybe give a default temperature of something in the area what we expect. What would be, maybe we expect something around 50 degrees. So this would mean the material properties of copper, if it is temperature dependent defined, then he will use the temperature of 50 degree to use the values from the temperature, from the material property definition. So, okay, so what are the conditions that we need? We need some loads, we need a current that we apply on the conductor, and we need a voltage on the other side where the current enters or leaves the conductor. Let's start with a current harmonic. Let's define this on a solid phase. Let's say here on this phase we apply a current, and we want to define this with root mean square, not with the amplitude value. So this is what we know, 1250 amps. This is our input current. And on the other side, here we want to define something like an opening, something like electric current going out. So, and this is done by a voltage of 0. So we go to a voltage on a solid phase, give this one, and say 0 voltage. So what else do we need? I blank these two. We need a constraint of flux tangent, a 0A pot, and this is normally simply applied to the complete outside of the simulation domain. So also this little one must be defined. So the complete outside of the simulation domain, because we want to define magnetic flux should not leave this area, so we define it to be tangent. So all the phases have this one. This is the constraint, so let's blank it. Okay, so now let's have a look into our copper parts, blanking the air. We additionally want to define now a resistance between these two conductors, an interface resistance. And so we say simulation objects, new simulation object, we define a contact resistance, one surface contact resistance. So, and here we define the interface region, so create a region. So here behind this face, on this face here, between these two, we want to have an additional contact resistance. And this additional contact resistance will have an effect on the electric field. So this is the most important one, the effect on the electric field. And we can define this now by an electric conductivity value and a thickness value if we want. But maybe it's easier to define this by a total resistance value. A total resistance value would mean we would give a total ohmic resistance that will be the loss value between these two conductors. And a value that we could maybe use is something like 5 micro-ohms. This is already quite a lot. And this can be found by measurements. Maybe we also want to have an effect on the magnetic field. So this means there's a small gap between these two conductors, and this also affects the magnetic field. This is not a very important effect now because we are working mainly in the electric area. Say OK. So that's it. We can solve the solution now and see what comes out. So here is our solution monitor from the magnetic solution. It's solving at 50 Hertz, and this is a very small solution. It should be done in about 5 seconds. It has already finished, so successfully ended, so we can have a look into the results. So let's open the results, double clicking here, and see what comes out there. These are our results. We see that there are integral values, so graph values for the copper 2, for the copper 1, and for the contact resistance. Let's check for the copper 2, make a plot, and we find out that there is a loss value of something around 17.5, here this value, in the unit watt. The first one has probably the same result. You see here, this one has also 75 watts. Yeah, it's okay because they are having the same size. And the contact resistance has an own result. So this means that this contact resistance in this area between the two conductors can also show the loss value. And this loss value is now something around 7 or 8 here watt. So it's also not so small, I would say. So these are the integral values, but we also have these plot values, of course. The first one is the electric potential. Let's look at the electric potential. Maybe we blank the air to having easier looking, and we also blank the elements. So this is how the electric voltage drops. We have a zero value here in the blue area, and we have a value of 0.133 volt at this location. So from this voltage drop we can, for example, compute the ohmic resistance or the impedance resistance. And we can, for example, have a look here at these two locations. If we check for this location and maybe for this location here, so between these locations we find we have a value of 0.066 and 0.069. So there is a small voltage drop between these two values, and this comes from the effect of the interface resistance. So if we would not have this interface resistance there, the voltage drop here would be much smaller, nearly zero. So this is our result, electric potential. Let's look at the next one, the eddy current losses density result. We have to activate the 2D elements for that. So here we see a loss value that we have to take care of. the eddy current losses density area. Check for the units. The units are in watt per millimeter square. Here at the bottom you see. So it is a loss per square millimeters. So this one must be taken to the thermal solver and to compute for losses coming from electromagnetics. And another one is this one, the eddy current losses density value. And this one shows us the losses on the 3D conductors. So you see these losses now, and the unit now is a watt per millimeter cubic, as you see here. Yeah, so it's a different unit type, and so we have to treat this one in a different way, or we have to treat these two loss values separately. To transfer these now to thermal, or just a second, let's first look to the last result, the magnetic flux density, and let's look in the air also. So here we see the magnetic flux density, and this is the typical result. Electric current produces a rotating magnetic field, and this is the rotating magnetic field that we see how it rotates around the conductor. Okay, but we wanted to check for the losses because they produce temperature. So here we have the losses of the 3D, and here we have the losses of the 2D geometry. Let's start with the 2D geometry. How do we transfer them to the thermal solver? We do this by creating a field. So right mouse button on the post view, go to create field from result and create a field. Let's call this losses 2D. So this is the losses that come from the 2D results. Say OK. And let's take the other one, the losses on the 3D with a different unit. Make another field. We have to do this separately because of these different units. So let's create a field from result again, and let's call this losses 3D. Okay, so you can have a look into your fields if you want. You see here fields, you have a losses 2D and a losses 3D field. Let's take one of them, for example this one, and go to edit, and you find here that there are all the locations stored, so an X and Y and a Z value, and a heat generation in the unit watt per millimeter cubic in this case. So all the locations are stored, and we can use this field now in the thermal solver as an input. And that's what we're doing now. So let's go out of this magnetic solution, and now let's think about the thermal solution. For the thermal solution, we first should go to the FEM file, make the FEM file visible, and switch the solver in the FEM file to thermal flow. So that means we edit this FEM file, and here we have the solver set to magnetics. And if we want to use another solver that needs other properties, we simply go to this one and go to the other solver. We, for example, want to use the thermal flow solver. Alternatively, you could also use the electronic systems cooling solver. It's nearly the same. So, and we want to have it not thermal, we want to have it coupled thermal and flow. So both thermal and flow is available. And if we do this, we have now the possibility to additionally give properties for the thermal solver. So we have to go to the air, edit the air, and now we have different properties because now he looks for the thermal flow properties, and so there are no our magnetic properties anymore. We have to again ask for a material, and now we go to the choose material because we want to take our material that is used for thermal flow, and we have to go to the libraries, for example, switch off these buttons and take the default library, and there's the air material that is of type fluid that can be used for thermal flow. Let's take this one and OK. For the copper, let's go to the copper. There we also have different properties now. We have things like radiation, for example, that were not available in magnetics. And there we also need a material. So this is the material that we want to use for the thermal solution. And we can use the same copper that we already have used for magnetics, because this one has also the important properties. So the properties that we need for the thermal solution are the thermal conductivity and the thermal capacitance, and these properties are defined here in this material, so we can simply use it. So take the same here for the copper one. Also use the copper material, and that's it. So now we have defined in this FEM file two solver properties. We have defined for the magnetic solver, and we have defined alternative properties for the thermal solver. Let's go back to the simulation. And now any of these solvers can be used here, because the FEM file has the properties for both of them. So we can now create a solution for thermal flow. Let's call it thermal flow, and let's use the solver thermal flow that is now possible. And let's go to the coupled thermal flow properties, thermal flow, and let's create a solution. And now you can define everything like you want in this complex solution here. You can define the turbulence models that you have here available. You can define here the solution type steady state or maybe transient. You can define all these outputs that are available. I want to define a buoyancy effect. So this means that the warm heat or the warm air will go into one direction. And the direction of the buoyancy is defined here in the ambient conditions. So the gravity direction, and you will see now somewhere there is this arrow now points into the direction of buoyancy. So this means the buoyancy is going in these directions, so the air wants to go up or down now because of this effect, this gravity effect. And what else do we want? I think that's it. For the simplest solution, we can simply stay with all the defaults here. Only buoyancy. Say OK. So what do we need for the thermal flow solution? Maybe let's start with our most important things, with the losses that come from magnetics. And the losses are defined as loads, as thermal loads. Always check for the units. The first one that is available here needs a unit of type watt, and we have other units. We have not the watt unit in our loss fields. So let's check for the next one, the heat flux value. This one wants units of type watt per millimeter square. So this one corresponds to our losses that come from this interface resistance. So let's use this one. So this means let's define the phase where this one will be applied. So this phase here in the between area, this is the one where we want to apply losses coming from magnetics. And we have stored these losses in a field, so we can now go to a field, select an existing field, and this one is the field that fits to this type of load. So only this one that we have called losses 2D is of this type. So let's use this one. We have now this losses 2D field applied to this phase. Say OK. So another one that we want to apply is a heat generation field. You see this from the unit. You see the unit that he expects now is watt per millimeters cubic, and this is what we have created from magnetics, the losses on the conductors. So this means we have to select now the polygon bodies, so this one and this one, and we have to say we want to choose an existing field, and there's only one available the one that we have named losses 3D. Okay, and that's it. So we have defined the losses on our 2D and our 3D geometry. Okay, so maybe I blank this one. What else do we need for the flow solution? We need to define opening. We want to define openings at the top and on the bottom for the air to go out or in. So let's go and make an opening. This is a flow boundary condition that is of type opening, and we say this one and this one are our openings. So that's it. And these faces where we did not define anything means there are wall faces, so the air cannot go out or enter. But for the thermal things, we should define something where the heat is going out, because heat is produced from this conductor in the middle, and we should define something like a convection condition on the outside faces. So on these 4 faces we should define convection condition. For example, a convection coefficient in these standard units of watt per meter square, something like 15 or so is a good value that we could use there. So that's it. And yes, we can now make a solve to this solution and see what comes out there. So we have now implemented the losses from magnetics going as loads to the thermal flow solver, and this is now solved. And the nice thing now in the solution monitor is to go to this Simcenter monitor, and this one allows us to check the results while it is solving. We can, for example, check for the fluid temperature here now while it is solving, and we see the changing of these results are shown to us in this solution control monitor. This is also available in this new version that we have here. And we see that the temperature is rising. It's already at 40.2 maximum value. And so this is, and on the other side, of course, we have these convergence control graphs where we can see that the residuals are already quite small, so it looks like the solution should be completed soon. Yes, and that's it. The solution is completed. We don't want to see these results, so we say no here. Okay, look into the thermal flow results here and find out the final results that we were interested in. We have a flow velocity. Maybe let's look at this one at the beginning. Flow velocity. So we see flow is going in these directions. Let's go to arrows. So let's remember it's positioned like this. So it's heating up from the conductor, and because of the heating, because of the buoyancy effect, the warm air wants to go up, and this is what it's doing. So it's going in this direction, and this leads to special behavior for the temperatures. So this is the velocity. Now we are, of course, interested in the temperatures, and blank the air to see only the temperatures. So, and this is what we have seen at the beginning. So our temperature result is now between 41 and 44, and if you want, you can also have an additional view here. The first one, for example, to show our losses, the losses density of this one, just to see here. these are our losses that we have seen. And in the second window we want to see the temperatures. Here, also without air and without 2D elements, and we want to couple them both, and this is what we wanted to see. Temperatures and temperatures resulting from electric losses in conductors. Okay. Thank you for your attendance. Bye bye.